Good evening. Over the next 5 minutes, I want to talk with you about how we can use nanotechnology to solve some of society's greatest challenges through an invention we call nanoparticle megalibraries. I want to do this in the context of the energy transition, but what I plan to tell you about is poised to impact every industry that relies on new materials. This is a major train that's coming down the tracks, and it involves a merger between nanotechnology and artificial intelligence. It is indisputable that we live in a world that relies on materials, and the discovery of new materials has led to what we refer to as civilization. Throughout the course of history, humans have gone from using stone for simple tools to forging metals to build structures, to the superalloys and semiconductors in our planes, cars, phones, microcontrollers, and even televisions. The Nobel Prize in Chemistry just went to the individuals that discovered the underlying quantum dot technology. With each advance, a new technological era is enabled. Now we've made it from the Stone Age all the way into the Nano Age, and nanomaterials, even though you can't see them, are already part of our lives, from zinc oxide particles in sunscreen to the palladium and platinum particles in catalytic converters, batteries, microelectronic devices, and solar cells. That's the good news. The bad news is that we discover new materials that matter at a snail's pace. The challenge is immense. It's not just a combination of elements from the periodic table that matter, but on the nanoscale, features like size and shape play an important role in defining the properties of a material. In other words, as a civilization, we have looked at a droplet of water in an ocean of near endless possibilities. With that in mind, some of the greatest challenges of our time, such as climate change, pollution, and the energy crisis, all depend on the discovery of new nanomaterials. We need materials that can help produce clean fuel, filter our pollutants, and capture and convert our greenhouse gases. For example, we produce megatons of CO2 each year, and in addition to coming up with ways to capture it, we need ways to transform it into something useful. We're at a crossroads here between two very different futures for our planet and life on it. So there is a certain urgency to this. We don't have millennia to discover the next set of materials that matter. And that means that we need to fundamentally change the way in which we discover new materials and do it at a rate that's never been done before. Here at Northwestern, we have invented nanoprinting tools that use the elements in the periodic table to print libraries of nanomaterials, just like we use the letters of the alphabet to print books and then libraries to store those books. In just a few minutes, we can use these tools to print millions of unique positionally encoded nanomaterials on a chip that's about the size of a nickel, a mega library. To put this in perspective, a single mega library contains more materials than everything we've discovered as a civilization since the beginning of time. This is only possible with nanotechnology. Even on the microscale, a chip like this would be the size of 2 Ryan Fields. Conservatively, there are about 10 to the 14th possible materials worth exploring. Try to imagine that number. Humanity hasn't produced 10 to the 14th of anything, except perhaps transistors, so this is an enormous challenge. But nanotechnology and the tools we have developed here make it a tractable problem for the first time. Now, making materials quickly in the form of mega libraries is only part of that challenge. We also have to figure out what these nanoscale materials can do. We need tools to read these mega libraries, like high-powered microscopes that tell us what these particles look like and ways to rapidly sort through them to determine which ones meet a given technological need, such as materials that convert CO2 into ethanol or ones that generate renewable hydrogen from water. One of the benefits of doing this is that the process of reading these libraries creates enormous amounts of unprecedentedly high-quality data that are perfect for training artificial intelligence algorithms. In other words, machines can be trained to help us sort through the vast number of possibilities to more quickly find the materials that matter. All of this requires a substantial multidisciplinary effort, and here at Northwestern, the IIN is bringing together the best people from all scientific disciplines, chemists, material scientists, engineers, and data scientists to collaboratively address this challenge. None of this is possible without a team effort. The university has been incredibly supportive, in addition to many wonderful people and organizations like the Sherman Fairchild Foundation and the Toyota Research Institute. I'd also like to personally thank the Ryan family for the fellowship that lets me do what I do. I am really proud to be part of an effort that is focused on solving a problem that will impact the vast majority of the world and lead to new ways to produce clean energy from renewable sources, capture our greenhouse gases, or solve the as yet unknown challenge that will undoubtedly follow. Thank you very much.